after that one important 8-bar set of all rigid motions of uh, an equilateral triangle forms an non-abelian group. That is an important 8-mark. Similarly, show that set of all rigid motion of a square forms an non-abelian group. These two problems are most wanted problem. 99% you may get 1 8 mark out of these two problems, either triangle or square. Okay, this is a most wanted problem in unit 1. Okay, now we are move into today class. Just we are going into today class. Okay, so today class, just I skip many of the proof of the theorems because some theorem already you studied in your plus 2 itself. Some theorems already you studied in discrete mathematics itself. Why I am skipping those proofs means these are all less important, because when you see the syllabus of unit 1, groups, properties, after that home cyclic group, then homomorphism. So most of the theorem belongs to symmetric group, permutation group, cyclic groups, that all important. For the remaining proofs and theorems, just go through it, not so much important. Okay, end of the unit I will tell you. So what are the important theorems, what are the important problem, which problems you are going to practice yourself. Okay, okay. Theorem, for every group, this is a property. So for every group G, the identity element of G is unique. Similarly, the inverse of each element of G is unique. If A comma B comma C belongs to G, if you choose 3 elements in G, that is A, B, C, and AB equal to AC, then B equal to C. This is called left cancellation law. Similarly, we have right cancellation law. BA equal to CA, then I can cancel A, which implies B equal to C. So these four are already you studied in school itself. I I took the school proof also. Okay, just go through it. This is the proof of an identity element of a group is unique. This is proof of inverse of each element is unique. This is proof of right cancellation law. Then this is proof of left cancellation law. Okay, because these all proof of those um, four things. Okay, so already you studied in school itself, just go through it. It's easiest one. Just we use the only associative axiom, inverse axiom, identity axiom, that's all. Okay, then the next one, reversal law. This is also already you studied in plus 2 itself. Let G be a group, A comma B belongs to G, then A star B whole inverse equal to B inverse star A inverse. Okay, this is also already you school in school itself already you studied. First line only I will explain. It is enough to prove that I want to show that A star B whole inverse, which is equal to B inverse star A inverse. That means B inverse star A inverse is the inverse element of A star B. The inverse element of A star B denoted by A star B whole inverse. So it is enough to show that B inverse star A inverse is the inverse element of A star B. What is the property? What is the inverse axiom? A star A inverse equal to E. A inverse star A equal to E. Both way you have to prove that. Okay. You can refer the proof easily. You can prove it. Okay. There is no difficulty. This is already you studied in DM. Show that any group G is an abelian. This identity is if and only if. This if is meet in if and only if. That means first I assume that G is abelian. Then I have to prove the identity. Then I assume this identity, then prove that G is an abelian. Already you studied this example in your discrete mathematics. Okay, so only skip this. So just see the proof. Okay. So consider G is an abelian. We have to prove this. easiest one. Okay, then consider the identity. We have to prove G is abelian. Okay, the proof is very easiest one. Where we have to start the proof, that is a important thing. So this is also another property. A inverse whole inverse equal to A in a group. In a group G, if we choose any element in G, A inverse whole inverse equal to A. This the proof of this theorem also already you studied in your plus 2 itself, DM also. Okay, I skip this. Please refer it. All are easiest one. Subgroup. What do you mean by subgroup? Let G be a group and H is a subset of G which is non-empty. So group means you have to choose non-empty. Subgroup means that is also non-empty. Okay. Let G be a group and H is a subset of G which is not equal to pi, that is which is non-empty. If H is a group under binary operation of G, one thing you have to keep in your mind, subgroup means the same binary of G for H also. Okay. So G is a set, there is a binary operation star. Suppose you want to say that H is a subgroup, H is a set whose binary operation is nothing but the binary operation of G. The both binary operations are same. Then only we can say that H is a subgroup. Okay, once I repeat, let G be a group and H is a subset of G which is non-empty. If H is a group under the binary operation of G, then we call H is a subgroup of G. So take a group, from that group means set with some binary operation. From that set I have to choose a subset. You want to show that the subset with respect to the corresponding binary of G is a group, then it satisfies the four axioms: closure, associative, identity, inverse. Then we can say that H is a subgroup of G. So trivial subgroups, if we choose any subgroup, the singleton E, the identity element itself, and G both are subgroup of given group G. So every group of G has singleton E, that is nothing but singleton identity element, and G are subgroups. These are trivial subgroup of G. The all other term non-trivial or proper subgroups. So each and every group has a two subgroup. Each and every group has at least two subgroup. One is the singleton identity element, the another one is itself. So those subgroups are called by trivial subgroup. The remaining subgroups are called by non-trivial or proper subgroups. We see the examples. In addition modulo 6 means Z6 comma plus 6. I can choose two subgroups, say H equal to 0 to 4, K equal to 0, 3, are proper subgroup of G, because identity element, that 0 is a subgroup, singleton 0 is a subgroup, the whole set, that is Z6 also a subgroup. So these H and K are is a proper subgroup. Okay, easily you can verify. All the axiom easily you can verify. Finally, we conclude that H and K are subgroups. Each of non-empty sets of 1, 8 and 1, 4, 7 are subgroup of union. Union means the set of all A such that the GCD of A, 9 is 1. That is the set of all relatively prime to A. The set of all number which is relatively prime to 9. That is the GCD of the member, and 9 is 1. Okay. So U9 is, we can say, the multiplicity group. U9 comma dot is a group. So 1, 8 is a subgroup of U9. 1, 4, 7 is also a subgroup of U9. U9 comma dot. The group Z plus 6. Z plus 6 means set of all integers with respect to addition is a subgroup of set of all rational number with respect to addition, which is a subgroup of set of all real number with addition. Okay. The symmetry group S4 consists of 24 permutations of 1, 2, 3, 4, because 4 factorial is 24. In S4, there is a subgroup of order 8 that represents the group of rigid motion of a square. See, we know that S4 is a symmetry group. S4 means there are 24 elements. What is subgroup of S4? That is nothing but the group of rigid motions of a square. This is a subgroup of S4. U9 is a subgroup of Z9 under multiplication modulo 9. So every multiplicative group is a subgroup of the corresponding. See, most of the cases, in generally I cannot say that because ZP, where P is a prime, in that case only multiplication modulo P, there is a group. It's form a group. Already I told that. Okay. But U9 not like that. Here I can apply for any integer n, but here I can only apply the prime number. Okay. So that means, so UP is any UP is a subgroup of ZP under mod P, under multiplication modulo P. I can generalize. Okay. So this is a theorem in this is an important theorem for discrete mathematics, not for algebra and number theory. This is one of the first proof. The theorem for proving subset is a subgroup of G. Just I read the statement. A non-empty subset H of the group G is a subgroup of G if and only if two conditions is enough. See what I told in the definition. Choose a group G comma star. From G I have to choose the non-empty subset say H comma star satisfied 4 axiom, then we can say that subgroup. But this theorem tells us no need to check the 4 axiom. It is enough to check 2 axiom. It's enough to show that the subset is a subgroup. What are the 2 axiom? The first one is closure axiom. The second one is inverse axiom. It is enough to show that closure axiom satisfy, inverse axiom satisfy, then directly I can say that the subset is a subgroup. Okay. So A comma B, if you choose any two element from H, that is A star B belongs to H. If you choose any element in H, the inverse element exists in H. That is, first one is closure axiom, second one is inverse axiom. If these two axioms satisfy, then directly I can say that H is a subgroup. Already you studied proof in your discrete mathematics. This is not important for algebra and number theory. So just go through the proof. It's easiest to prove. See each and every proof where I have to start. See here I proved closure axiom, associated axiom, identity axiom. From condition number 2, easily we can assume that the inverse axiom satisfied. So finally the theorem is over. Okay. So here carefully you have to listen the theorem. If and only if means I have to first assume H is a subgroup, then these two conditions are satisfied. Then these two conditions are satisfied, then I have to show that H is a subgroup. If and only means before the word if and only if, I can assume after the word if and only if I have to prove. Okay. Otherwise, after the word if and only if, I have to assume the content, then I have to prove the words that is before if and only if. Okay. I have to assume H is a subgroup, I have to prove this condition. Otherwise, I have to assume the condition, I have to prove the subgroup. This is the meaning of if and only if. This is another important one, cyclic group. Cyclic group. A group G is called cyclic if there is an element A in G such that G is equal to A power n such that n belongs to Z. Such element A is called generator of G. Simply I can explain. Cyclic group means, first of all, it is a group. First of all, it is a group. The whole group, the elements of the group, all elements of that group generated by a single element or more than one element. This is called cyclic group. Okay, clear? Cyclic group means a group generated by a one or more element. This is called cyclic group. That is definitely the whole set of elements of the group generated by a single element or more than one element. That is called cyclic group. Okay. The example, you may think that, do you have any doubt in the definition? Anyone reply me? Once again I reply, Because last 1 year back, uh, I understood the definition properly just 1 year back. Okay, because when you see the definition, I will explain. Once I will explain the definition, then what I did mistake in the definition, what I learned from the definition, I will explain. Okay. So what do you mean by cyclic group? First of all, you have to take a group. Each and every element of the group generated by a one element or more than one element, then we can say that that group is cyclic group. This is the definition. That element is called generator of that group. Okay, this is the definition. So note my word, each and every element of G generated by an element or more than one element. Okay, this is called cyclic group. Do you any doubt in this definition? Anyone reply me?
No, sir.
No, say Sanjay. That means cyclic group has in have only one generator. So each and every cyclic group has at least two generators. You have to keep in your mind. Each and every cyclic group has at least two generators because, sir, you told that two generator, but in the definition you write only one A. That means if A is a generator of a cyclic group, then the inverse of A inverse also generator of a cyclic group. Keep in your mind, if A is a generator of group, then inverse of A is also a generator of group. You have to understand this concept. A is a generator of group, the A inverse also a generator of a group. Keep in your mind. Okay. Sometime some cyclic group has only one generator. There is a possible. Just I get back my word. That is, some cyclic group has only one generator also. How is it possible? In early case, I told that each and every cyclic group has at least two generators, but I get back my words. Now I say that the cyclic group has some cases the cyclic group has only one generator. Such such type it exist? The previous time I told that each and every cyclic group has at least two generated. Suddenly I get back my words, then say that some cyclic group has only one generator. Is it possible? How you say each and every cyclic group has two generator? If a number is generator, then inverse also generator. So only I told that at least two generators exist for each and every cyclic group. But now I get back my word. I told that some cyclic groups may have only one generator. Is it possible, Sanjay? Say yes or no.
Sir, I don't know, so maybe, sir. So
Maybe.
this group, so G is equal to I comma minus I comma minus 1 comma 1.
In that case,
I think it has only one generator, which is I.
no. minus I also generator.
Yes, sir. Okay.
I and minus are generator. Okay, because I and minus are inverse of each other.
But then if we want to find the inverse, we have to bring it under binary operation, right? So
No, not
we don't
right.
have the binary operation.
No, no. Ujjwala, is it possible of a cyclic group getting only one generator? Is it possible?
I don't know, sir.
You don't know. Okay,
Think
okay.
it's not
Any?
possible.
Okay. Not possible. I cannot told that I get back my words. Okay, okay, I will explain. Ansul from section A. There is any possible? Balaraman from section A. Okay, is it possible? Because sometimes inverse of element is itself. Sometimes the inverse of element is itself. That is, if you choose U8, U8 is a multiplicative group. In that case, uh, in that case, you can the elements are U8 means relatively prime to 8. That is 1, 3, 5, 7. In that case, 3 is a generator. 5 also generator, okay, no problem. But sometimes a element, its inverse, suppose 3 is an element of U8 means the inverse of 3 itself, that is a possible, okay. Inverse of A is itself, that is a possible. In that case, a cyclic group has only one generator. Did you understand what I said? Suppose the inverse of element, suppose inverse of 2 is 2, then in that case we have only one generator. Inverse of 2 is 3, in that case we have two generator. Did you understand? Did you got my point? Did you get my point?
Yes, sir. Yes, sir.
Okay. So only here they give the set is generated by a single element, at least single element. Sometimes it is possible of getting two elements. The best example is set of all integers. Set of all integer with respect to addition. What are the generator? Now tell me. இத நான் ஓப்பனாவே சொல்றேன், இந்த டெஃபினிஷன் இது வரைக்கும் நானே வந்து ஒரு ஜென்ரேட்டர் தான் நினைச்சிட்டு இருந்தேன். ஈவன் லாஸ்ட் 1 year பேக் my dealing with my research papers, then only I conclude that this is not a one. The meaning is not a single generator. There is a possible of at least two generator. The inverse element has inverse itself. In that case, only one generator. Okay. So the example, simple example is take a set of all integers with respect to addition. Now tell me what are the generator. Okay, I can classify into two parts. One is set of all positive integer, another one is set of all negative integer. What is the generator of the set of all positive integer? Which element generate all the positive integer with respect to addition? Generator means, see here a power n. For multiplication, I can apply a power 1, a power 2, a power 3, a power 4. With respect to addition, a square means a plus a cube means a plus a. Okay, so the set of all positive integer generated by plus 1, the set of all negative integer generated by minus 1. Okay, set of all generator is the set of all negative integer, set of all negative integers generated by minus 1. So G is an identity element. So this is in the case of two generator, but one is a generator, minus one is a inverse of one, so definitely that is also generator. Okay, so one of the beautiful example is set of all integers. Here there are two generators, say 1 and minus 1. Okay, so now we can see another example. A group G is a cyclic group generated by A and it is denoted by G is equal to this is a notation. Okay, so less than symbol A, greater than symbol. Okay, that means each and every element in G generated by a single element A. That is a meaning. Okay. So one of the beautiful example is Z8. Z8 is nothing but so here 1 is a generator, 3 is a generator, 5 is a generator, 7 is a generator. There are 4 generators. Okay. Then U10 means relatively prime to 10. So 1, 3, 7. So 3 and 7 are generators. Next, order of an element. What do you mean by order of an element? Let G be a group and let A be an element of order n in G if A power n equal to E. Okay, that means simply I can explain. Suppose you want to find the order of an element, just raise the power of the element, wherever get the identity element, that power is called by order of an element. Choose an element from your group, then raise the power, a power 1, a power 2, a power 3 and so on. Wherever you get the identity element, that power is called by order of an element. So here the group G is equal to, this is fourth root of unity, 1 minus 1 I minus I is obviously cyclic group. So generators are I and minus I. So there are two generators. The set Zn, that is Zn means if we choose any n under addition modulo n is a cyclic group. The generators are obviously 1 and n minus 1 are generators. 1 and n minus 1 are generators. This is important 2 mark. What is the generator of Zn means 1 and n minus 1 are generators. Suppose for particular case you may have more than one generator. For particular case you may have more than two generator. In Zn generally I can say that if you choose any two element, at least 1 and minus 1, 1 and n minus 1 are generated, but some cases you may have more than two generators. This is some important 4 mark. Let A belongs to G with order of A equal to n if K belongs to Z and A power K equal to E, then n divides K. That means I will explain by words. Suppose if you choose any element in G, the order of A is n. If you choose some other element in set of all integers, then A power that element is equal to E. That is, order of element means A power, see here order of A is n, that means A power n is E. Order of A is n, so I can which implies that A power n is E. Suppose some other integer K belongs to Z such that A power K is E, then definitely that K is divided by n. In other words, n divides the K. Okay. Did you understand? So this is meaning. Suppose the greatest common divisor. So what do you mean by greatest common divisor? Common divisor, which is the out of which we have to choose the greatest number. If we choose some other integer, also a common suppose we can say that common integer, definitely the greatest common divisor. Suppose you can say that some other number is the greatest common divisor. Definitely the original number divides that number. So that means the order of an element is the least power of A such that the answer is E. The meaning of the theorem is A power something is E. We know that. Okay. So order of A is n means n is the least power. A power n is E. If we choose, suppose if we get any other A power is E, definitely that power is divided by n, or the n is divides that power. N divides that power. Okay. The proof is very simple one. Let us assume that by contrary method, let us assume that n does not divide k. N does not divide k. By division algorithm, already I told that n is the smallest number, k is the biggest number. Okay. So by division algorithm, we have k equal to qn plus r, because k is a dividend, n is a divisor. So by division algorithm, k is equal to some quotient q, some remainder r, and k equal to q1 plus r is varies from 0 less than or equal to r less than n. Consider, because we have a power k equal to e. So I start from e equal to a power k. By division algorithm, I can replace k as q power n plus r. I can split it a q power n into a power r. Here I can rewrite a power n whole power q. Then we know that a power n is e because order of a is n. So I can a power n replaced by e. E power anything is e because identity element power any number is an identity element. So e into a power r is equal to a power r. What is your r? What is the definition of here? I didn't write 0 less than or equal to r less than n. That means what is the definition of order of an element? A power n equal to e means n is the least integer, but here r is an less than n. That means I can able to find the integer which is less than n such that a power r equal to e. This is contradiction to the definition of order of an element. So why I got this contradiction? If I choose the remainder, if we suppose when you divide k by n, I assume that there is a remainder exists. So then only I can get the contradictions. That means I have to choose r equal to 0, which is a contradict to the definition of n as order of a. So hence, why I got this contradiction? I assume that I got the remainder. So only I got the contradiction. So I can assume hence r equal to 0, which implies k equal to n qn, which implies n divides k. So the proof is over. So examples. So this is take g is equal to 1 minus 1 I minus I. Definitely you know that this is an abelian group. Order of I is equal to 4. Easily you can verify. Order of, if suppose if you get any other power is 1, no. I power n I power 2 minus I power 2, that is I square is minus 1, I power 3 minus I power 4 only you can get 1. So there is a chance of getting any other power of I is 1, definitely. The multiples of 4, definitely you will get 1. That means 4 divides 8. 4 is a least integer. I power 4 equal to 1. Therefore, if we get any other power of I is 1, definitely 4 divides that number. So already I told that the most important problems are set of all rigid motions of a triangle form and non-abelian group, set of all rigid motions of square form and non-abelian group. Those two problems are very, very important problem. This is a most wanted theorem in first unit. This is most wanted theorem in unit 1 because this theorem belongs to cyclic group. In the syllabus itself they mention cyclic group. So this is most wanted important theorem. Okay, please listen carefully, then only you can easily understand. Otherwise, because there is a problem in Google Classroom, so only I cannot send your videos for previous classes. Once you get the video, repeatedly you can see this video, easily you can understand the theorem. Okay. Otherwise, just follow my words now. Easily you can understand. What is the theorem statement? Every subgroup of a cyclic group is cyclic. Every subgroup of a cyclic group is cyclic. So this is an important theorem. So we have a cyclic group. I have to choose a subset from the cyclic group. Then I have to show that that cyclic group, that subset is form a definitely there is a subgroup of the cyclic group, but I have to show that that subgroup is again a cyclic. So every subgroup of cyclic group is cyclic. I want to show this. That means you know that cyclic group means each and every element generated by a single element. Okay, okay, a power n. The form of the cyclic group is a power k or a power n. Okay, but if you choose a subgroup, say some element, so all the elements also generated by a single element. All the elements generated by a single element. That means, suppose I choose an element from H, say K or say B. Okay. Suppose I choose I have a cyclic group. I have a cyclic group. From the cyclic group, I choose a subset. From the subset, or I can choose a subgroup. From the subgroup, uh, from the subgroup, I have to collect one element, say A. So each and every element of the subgroup generated by that A. That means each and every element of the group in the form of A power something. Then only we can say that the subgroup is generated by A. But keep in your mind that subgroup that is the subset. The subset is nothing but we get from G. The G is a group. G is a cyclic group. So each and every element of a cyclic group has the form, say some B power, some power, B power, some power, that is B power T and so on. So what I'm going to do is, if you choose a subgroup, I assume I can take one element, that element has a form of B power T because B power T is, because G is a cyclic subgroup. G is a cyclic subgroup in each and every element has a form B power T. So I choose a subgroup from G. So definitely each and every element has the form B power T. Okay, what I'm ultimate aim is the elements of H is generated by B power T. The element of H is generated by B power T. Then we can finally we prove that B power the H is the subgroup is a cyclic. Okay. Once again I repeat. Please listen. Once again I repeat. G you have to carefully understood. We have a cyclic group. We have a subgroup. Okay, we have a subgroup. You understand my words. We have a cyclic group. We have a subgroup of that cyclic group. My aim is I have to prove that the subgroup is cyclic. What is the meaning of cyclic group? Each and every element is generated by a single element, say B. That means each and every element of a cyclic group has the form B power T. Okay. So I have a subgroup of the cyclic group. So each and every element of the subgroup has the form B power T. Has the form B power T, because cyclic group has a form, each and every element of the cyclic group has a form B power T. The sub elements of the subgroup is nothing but elements of the G also. So each and every element of subgroup has the form B power T. But I have to show that the subgroup is cyclic. That means each and every element of the subgroup has the form B power T. Okay, so each and every element of the subgroup has the form B power T some power, B power T some power. Then finally we can say that the subgroup is generated by B power T, therefore that subgroup is cyclic. This is my ultimate aim. Okay, so each and every element has the form A power something, the power is T, T is varying. But I am going to prove the subgroup is a power of B power T whole power. That power is varying. Okay. Okay. Please listen. Why I am explain lot of thing means why I am repeating many times is this is the most important thing. Easily you can understand. Okay. Let we know that G is a cyclic group. That means G is generated by a single element A. That means each and every element of G has A power something. A power something. Okay. If H is a subgroup of G, because we know that H is a subgroup, each element of H has the form A power K, because each element of G has the form A power K, which implies definitely H is a subgroup whose elements belongs to G. G has the each and every element of G has the form A power K. So definitely each and every element of H has the form A power K for some K belongs to Z. The power is nothing but integer. Okay, did you understand that this two statement? G is a cyclic group which is generated by a single element. That means each and every element has the form A power something. Okay, some number. H is a subgroup of G, so each element of H has the form A power K for some K belongs to Z, because the elements of H is also elements of G. Okay, H is a subgroup of G. For H, I can choose an identity element. For H is not equal to singleton E, because singleton E means definitely is a subgroup, definitely is a cyclic subgroup. Singleton E means definitely subgroup, definitely is a cyclic group. So only assume H is not equal to singleton E. Let T be the smallest positive integer such that AT belongs to H. So each and every element of H has the form A power K. But I choose some element A power T belongs to H. Okay, the T is the smallest positive integer. Okay, because in H there is a power A power T1, A power T2, A power T, A power T1, A power T2, A power T3, A power T4 and so on. But the T is the least positive integer. Okay, I assume that A power T belongs to H such that T is the smallest positive integer. The claim H is generated by A power T, because what is my claim? If I show that H is generated by A power T, then the theorem is over. So here G is generated by A, but here I want to show that H is generated by A power T, because each and every element has the form A power some number. So definitely the subgroup is generated by A power some number. Okay, because G is cyclic. Since A power T belongs to H, we assume that A power T belongs to H. A power T belongs to H by closure property for subgroup of G, because we know that H is a subgroup. So closure axiom is subgroup. So A power T belongs to H means A power T into A power T also belongs to H, that is A power T whole square. A power T into A power T into A power T, that is A power T cube, A power T whole cube, that is also belongs to H by closure axiom. Therefore, each and every element generated by A power T, that is also a element in H. So I can say that the elements generated by A power T which is contained in H. By closure axiom, I can easily say that the each and every element generated by A power T which is contained in H. Okay, because by closure axiom. Closure axiom means if we choose any two element, then multiply the resultant also in H. We know that H is a subgroup. So element in H is A power T, definitely A power T into A power T also in H. Okay, my ultimate aim is the A power T is each and every element generated by A power T. Okay. So if I choose some other element in H, randomly I can choose some other element in H with, so I already told that each and every element in H is some power, some A power something, because it's an element of G also. So I can take an element in H, say B, which is nothing but has which has the form B equal to A power S for some S belongs to Z, because each and every element in H has a form A power something, because this is a element in G, since G is a cyclic group. So B is equal to A power S. By division algorithm, I assume that S is n greater than T. Okay, I choose that this is belongs to B. Okay, so I assume that the power S is greater than S, because we assume that T is the least element. The element A power T, where T is the least element, so definitely this S is greater than T. So by division algorithm, this S is greater than element, bigger number, T is the smallest number. Apply the division algorithm. S equal to Qt plus R. Q is an quotient, R is an remainder. The range of R is 0 less than or equal to R less than T, because T is a divisor. Consequently, I can consider A power S. I can replace S as Qt plus R. Then I can split it A power Qt into A power R. I can keep A power R in the right hand side, then keep A power Qt in the left hand side. So A power R equal to A power minus Qt into A power S. I can read it A power minus Qt is A power T whole power minus Q into A power S. Okay, this A power is nothing but my B. So A power T whole power minus Q into B. So finally I show that A power R is equal to A power T whole power minus Q into B. H is a subgroup. So if A power T belongs to H, definitely A power T holds some power, definitely also belongs to H. A power T belongs to H, definitely A power T whole power minus Q also definitely belongs to H by closure axiom. Then the previous case, see that we have a product of two number. Now I shown that this is belongs to H. So this is belongs to H. We know that B belongs to H. Definitely the product also belongs to H. The product is represented as A power R. So A power R belongs to H. Okay. What is the R value? R is lies between R is less than T. So already we assume that A power T, where T is the least element in H, but now I have A power R belongs to H, where R is less than T. This is contradiction. If A power R belongs to H with R greater than 0, then which is contradiction to the minimality of A power T, because if we choose any element in H, the least power is T, but here I have the power which is R, which is less than T, so which is belongs to H. This is a contradiction, because I got the smallest element compared with T, which is belongs to H. Okay, so this is contradiction. Why I got this contradiction? I assume here, when you apply the division algorithm, I assume I got the remainder. Then here I assume I got the remainder, so only I got the contradiction. So finally I can assume that my remainder is 0. So what is will be A power Qt, because what is the B represented as A power Qt plus R. Finally I got B is equal to A power Qt plus 0, which is equal to A power Qt. I can read it A power T whole power P whole power Q. I randomly choose the element B which in H. Finally, I show that that element is in the form, that element is generated by A power T. This is conclusion of that A is n cyclic. So first I assume that I pick an element, the form A power T, whereas T is the least element in least value in H. Okay. If I choose randomly some other element in H, finally I show that that element is as the form A power T whole power Q, that is that element is generated by A power T. Finally we can conclude that H is generated by A power T, that is nothing but cyclic, therefore H is an cyclic subgroup. See, where I randomly I can pick one number. See, already I choose a single element. Randomly I can pick now pick some number. Finally, I show that that number is generated by a power t means if you choose any element in H, definitely that element is a form. That element is generated by a power t. Therefore, I conclude that a is equal to the generator of a is equal to a power t. Hence, a is an cyclic subgroup. This is most wanted theorem. This is most wanted theorem. What I said, the last two problem, 19%. This is also most important problem. There are three theorems. Cyclic subgroup of cyclic is cyclic. Finite group with prime order cyclic. One more theorem I forgot. I will tell you later. Okay. So this is the most important theorem. Please, if I get the video, please see many times. Okay. Then only you can get the idea. Okay. Okay, man. Thank you, man. Thank you. Now you can leave the class. We will meet in third section.